Hi, my name is Dan, and this video is one in quite a long series of videos which are using digital logic gate simulation software to create a 4-bit CPU that is programmable and works, which is quite interesting. So there's a roadmap of where we're going in the description down below. There's also a link to the digital hardware simulator that I'm using called Digital Works, but this video and this shorter series within the larger series are not actually diving into that. We're talking about the design of the CPU that we're creating. Everything is now got very specific to this particular 4-bit CPU. In the previous video, we just designed the opcode set. Before that, we talked about some general principles. And design decisions. And if you wanted something that was more generic about CPU design in general, then this may not be the most helpful thing that you wanted. But if you want to have some understanding of CPUs and how they work and how the hardware behind them is wired together, then you might need to take the series as a whole, but this is part of that process. And in this video, I'm going to do a roundup of the hardware components that are going to go into our ALU. Sorry, CPU. I'm getting my acronyms mixed up. So CPU, Central Processing Unit, is the larger thing that can be programmed to perform operations. Here we go, components list. We've got a number of registers that we're going to need. We've got MAR, which is the memory address register, MDR, which is the memory data register. We've got A and B, which you could think of as general purpose registers, but they're actually the input registers for the arithmetic logic unit, which is ALU. ALU-X is the result of a calculation. ALU flags are extra information about the calculation that's happened in the ALU. PC is a program counter to help us keep track of where we are in our program, which is being held in the memory bank. PC is going to be a special register, but we'll deal with that later. Op is a register to hold the current operation, the opcode for what we're currently doing, and data is a register that's going to hold extra information. This hopefully will make more sense now that we've gone through the opcodes, is that for some of the operations you need to know an address in the memory to read from or to write to, or it can be a data number, so what's called a literal, which we're bringing into play. Okay, that's, I believe, a full list of all the registers that we're going to need in the CPU. And the other stuff, we need an ALU, of course, which is the arithmetic logic units. We're going to need a memory bank, which is connected. I haven't listed a bus here, but we're going to need that. That's not really hardware in the same sense because it's just wires. And we're going to need a control unit, which is actually going to be the most complicated thing that we make because that is going to take the operation that's in the op register and mediate between all the other bits of hardware and the registers to make things happen. There's one thing that we're going to need that I haven't mentioned, and that's because we haven't talked in detail about the fetch execute cycle yet. But one thing that we're going to need in order to make that happen is a thing called a ring sequencer. This is actually a fairly simple piece of hardware, but you won't understand the need for that yet. I'm just going to talk about that in the next video when I'm going to go into more detail in the fetch execute cycle. Anyway, other than that, throwing that in, there's actually no new information in this video other than kind of a recap of where we're going and what we're going to need to put together. How they're put together is also something that we need to talk about in a future video, but we're coming to it. Keep working your way through. Next up, talk about the fetch execute cycle and this thing called the ring sequencer. But that's it from me for now.